So in study unit 1, you've got a basic introduction into your amplifier. So they take your amplifier and they break it up into stages, your input stage and your output stage. This is done to illustrate the concepts of loading. Because your amplifier is not a perfect circuit, it has losses, you get loading. Your input loading factor is how much the input is loaded, and your output loading factor is how much the output is loaded. So when it comes to your amplifier, you've got 4 different combinations that are made out of these 4 stages here. Right. So our input stage can either have an input voltage or an input current, right? And then our output stage can either be, let's use blue. So output stage could either be an output voltage or an output current, right? So your output gain is dependent on which combination of these 4 you are going to be using, right? So with a voltage amplifier, as shown in this gain, your voltage gain is your V out over your V in, right? So that is a combination of stage 1 and 2. For your current amplifier, you've got I out over I in. This, right, which is a combination of 3 and 4. From there, you can also combine them like this or like that to get your transimpedance and transconductance amplifier. So for transimpedance, you know that your resistance is V over I. So that means you need an output voltage and an input current. So therefore that is just stage 3 and 2 together. That would be your transimpedance amplifier. And for transconductance, it's the opposite. So transconductance is output current over input voltage, which is just stage 1 and stage 4. That's your A of GT. And put this as A of R. So those are your 4 gains, right? And this is how you get your 4 gains. So your loading factor is basically either a current division or a voltage division, based on which of these 4 stages make up your amplifier, one of your 4 amplifiers. So if you've got a voltage gain stage, like this stage or this stage, then your input loading factor and output loading factor are shown by those. That's basically just a voltage division. How much of the input loading factor and output loading factor, when it comes to a voltage part of the voltage stage, is how much of the input voltage from here or from there is delivered all the way to your output. And for your current stages, it's a current division. How much current is delivered here? Okay, maybe that's a little bit. So it'll be how much current is delivered here versus this input current here. Those two. So, and that loading factor is described by that equation. That is just a simple current division equation. So that is basically study unit 1. You should have seen everything that happened here. These are just your stages of your amplifiers. In study unit 2, they introduced the concept of saturation, right? So saturation occurs because in your amplifier is made out of discrete components, so therefore there's going to be voltage drops, therefore you cannot reach the peak rail to rail output. So saturation is usually stated by a single digit, right? But the one thing that some people don't understand is that saturation gets applied to your positive and your negative rails, not just to your positive rails. So whenever you're designing an amplifier, you should take your saturation into consideration, and those are things that are usually covered in your practicals. So there won't be too many saturation questions, right? And then after that, they have a brief ELI revision, a recap. So from here, what the most important thing is that in ENE, you do not draw board plots, but you expected to analyze the board plots. So you have two typical responses. You've got your low pass response and your high pass response, right? So your low pass response comes from this circuit here. In electronics, we avoid using inductors because as you get bigger inductors, they become bulky and they cause harmonics. Inductors are just problems. So most frequency dependent components are usually capacitors. So that's why we always use capacitors to do the low pass and the high pass, but you can also use inductors. So with your low frequency, because your capacitor is open at DC, you get a voltage output, and at high frequency it becomes a short, so that's why it starts cutting off there. And at high frequency, it's open for your high pass, it's open at low frequency, so you've got no output, and then at no output shown by there, and high frequencies becomes a short, so therefore you got a voltage output, which is where this comes from. That was just some basic revision. This is important because when you get to the filter section in multiple choice, they do have a tendency of giving you filters with configurations that you haven't seen before. So therefore you're going to have to be able to analyze your filter and make an educated guess about what it is, checking on what it does in the low frequency, mid band, and high frequency. So here there's not really much that's going on other than the dominant pole discussion. So the one thing about the dominant pole is you need to ask yourself this question: is there one pole that controls the whole cutoff, the whole frequency response of this amplifier? So the way you check for dominant pole is that one pole must be one order of magnitude away, right? So one order of magnitude usually is about 10. So if you've got 1, 20, 50, your dominant pole is 1. Your dominant pole is always the first pole. It's either the first pole, it's not. So if this was a case of like 1 to 100, you can't call this your dominant pole because your dominant pole is only your first pole. And because these are only separated by 2, this would mean that this is not your dominant pole also. So when we say a magnitude, this value of 10, we're talking about 100 over 10, 1,000 over 10. So the ratio of the second pole to the first pole must at least be 10 for you to consider that pole to be a dominant pole. And that's basically dominant poles. That's SU2. Just revision of your ELI board plots. Remember that you won't be asked to draw board plots, but you'd be expected to know how to analyze a board plot. And the discussion on dominant poles. And remember that dominant poles must be a order of magnitude greater. So that means it must be at least 10 times greater for you to consider it to be a dominant pole. And